Hello, this is Investigating Shooting Strategies based on a nested Faraday cage design. This is a project under RAU. My name is Treat, I am the team leader, and to start it off, I'm going to hand it off to Kim.
So first of all, let's dive into the nanopore sensor. Nanopore sensor in our system examines the behavior of light going through a nanopore in the picoamps scale. We ensure functionality of the sensor while minimizing the RF leakage. Nanopore sensors are highly sensitive to electrical, mechanical, and optical noise. So as you can see, the picture on my left is the previous cage iterations, and the one on the right is our current nested Faraday cage design for this project. So our goal is to develop an effective and economic solution for shooting the nanopore sensor. These aspects must be considered for designing picoamps level electromagnetic blockage, post-collection signal processing, proper grounding, harmonized mechanical structure, and light attenuation. Our cage is built from an aluminum frame with very thin aluminum sheets with an added layer of Faraday cloth followed by audio foam. The inner cage is made as a multi-layer shield from inside to outside. It consists of ESD foam, high-density anti-static foam, wire mesh, copper mesh, Faraday cloth, three additional layers of copper mesh, and a final layer of Faraday cloth. This multi-layer nested design combines conductive metals, anti-statics materials, and foam layers to strengthen EMI shooting and better protect low noise measurements.
Okay, so I'm going to talk about the purpose of the analog filter within the Faraday cage system. And so the purpose of the analog filter is heavily tied to the important information that is embedded inside of the transient peaks of the nanopore curve signal. And so these peaks tell us a lot of important information about the molecule that is passing through the nanopore curve sensor. These signals also do introduce a lot of baseline drift. And so what ends up happening is these baseline drift can actually overlap the subsequent transient peaks of the nanopore signal. And so what ends up happening is we lose a lot of important information about the following transient peaks. And so the purpose of the analog filter is to attenuate the baseline drift. That way we can retain very important information about the transient peaks of the signal. This is done through RLC topology. So this is a resonant circuit that you essentially apply a target frequency, and it will effectively attenuate the frequencies around that target frequency. And so in the case of the nanopore curve signal, we want to eliminate the low frequency components that are associated with the baseline drift of the signal. Here is the nanopore curve comparison. The top filter, the top graph is the nanopore curve signal with the filter. And so you can see the signal that returns effectively back to baseline. And the bottom plot is the nanopore curve signal that doesn't have a filter. So you can see the signal drifting off and never really returning back to baseline at all.
Going over the main testing method we use for this project, we use something called an IV sweep. I stands for current and V stands for voltage. Basically, we send a voltage rectangular pulse to our system. We send a bunch of them ranging from negative 400 millivolts to positive 400 millivolts. And by measuring the current, we can analyze the transient response of the system that had against a pulse signal. It's a current SNR comparison with an open Faraday cage and a closed Faraday cage. The blue one is the one with the closed Faraday cage, and the red one is the one with the open Faraday cage. And as you can see right here, the SNR of the nanopore with the closed Faraday cage is performing a lot better than one with an open Faraday cage, proven by the fact that there's around 10 decibels to 11 decibels difference between the closed one and the open one. This is the current SNR comparison between different nanopores. We have a 30 nanometer nanopore, 122 nanometer, 315 nanometer, and a 200 nanometer nanopore. It's good to keep in mind that the 30, 122, 315 nanometers nanopore experiments are done with the new cage while the 200 nanometer one is done with the old cage. Using some extrapolating and estimating, we find out that the 200 nanometer nanopore SNR for new cage would be around 0.2 decibels. And comparing this to the old cage, which is around negative 8.42 decibels, we found out that the new cage would be performing around 6.6 times better than the old cage. Last but not least, one of the smaller but also important tests we did is light attenuation. Since the nanopore sensor is so sensitive to light, we take out the material used to build the Faraday cage, shine a light to it, and get a percentage of light that's reflected back from the material. As you can see on here, the percent only or less than, for most of them, only less than 0.1% of the light is reflected back to the sensor that we use. So this is very manageable for our nano sensor. Using all these tests, we come to the conclusion that this Faraday cage design proves to be a lot more effective than a single layer copper mesh Faraday cage design, the old one we have, and obviously is a lot better than having no Faraday cage at all. This design, a nanopore sensor can operate at 100 millivolts without being overweighted or drowned by noises. And using this Faraday cage design, it can suppress this unwanted noise enough to the point where our analog signal filtering is work enough that allows transient peaks to be properly conditioned for clean data acquisition.